Every day, blast furnaces around the world swallow tens of thousands of tons of a black rock. That's coking coal. Feeding a beast that hungry means moving mountains, running trains on port schedules, and baking coal at 1,000 degrees for hours without letting anything cool. I will walk you through the whole chain. The final piece closes a loop nobody talks about. A blast furnace can burn through tens of thousands of tons of coking coal in a day, and every ton of it started at a place that looks nothing like a factory. It started at a hole in the ground the size of a small town, in the Hunter Valley, where the shift change happens under floodlights. Before anyone gets near the coal, they have to move the rock sitting on top of it, and the numbers get silly fast. A 2-excavator fleet at this site pulled 1.752 million bank cubic meters of overburden in 1 month. That is dirt and rock, not coal. All of it moved just to expose the seam underneath. Each excavator weighs 800 tons. I keep telling people that number and I can see their brain buffer for a second. 800 tons on tracks, running 4 pass loads into 320-ton class haul trucks, cycling under 302 seconds a bucket. The trick is not the size. The trick is keeping something that heavy running around the clock without breaking. Try phoning a wrecker for an 800-ton excavator and see how that conversation goes. So the whole operation runs on proficiency training, cleaner engine repowers, and cycle times that hold up at 3 a.m. Overburden work does not stop at the excavator. The trucks and dozers behind it are what turn one bench into a working pit. At a surface coal mine south of Frostburg, Maryland, haul trucks and dozers run in tandem. Loaders fill the trucks at the bench, dozers keep the working face pushed forward, and the whole cycle repeats until the seam underneath is exposed. A set of 6 haul truck tires can run north of $100,000. That is not a typo. That is the ticket for one truck's shoes. Not every rock in that pit is going to make steel. Most of it is not even close, and the sorting starts long before the first truck rolls out. The answer to where coking coal actually comes from starts with a map most people have never opened. In the Hunter Valley, a single open cut sits on 242 million tons of reserves and permission to keep going until 2039. 5 main seams, 17 plies of coal stacked inside them, and a drag line swinging over the pit around the clock. 15 million run-of-mine tons a year. Not every coal basin gets to sell to steelmakers, and Queensland's Bowen Basin is one of the few that does. A pit outside the town of Moranbah is designed for 3.6 million tons of raw coal a year, feeding a wash plant that spits out about 2.8 million tons of finished product. The overburden numbers are where it gets absurd. 14 million bank cubic meters of waste rock moved per year, mostly by a drag line with a 49 cubic meter bucket, backed by 4 truck and excavator fleets and 5 of the biggest dozers Caterpillar builds. Here's the part nobody outside the industry ever asks. Why bother sorting if the coal comes out the same color? Because it does not. The finished product splits into semi-hard coking, semi-soft coking, and thermal. 3 different customers, 3 different prices. Get the mix wrong and the whole shipment sells at a discount you cannot argue your way out of. Bigger operations show what a strip ratio actually costs you. At the Blackwater mine, a life-of-mine strip ratio around 12 means 12 tons of rock get moved for every 1 ton of coal reached. 7 drag lines work 8 separate pits at the same time, digging 45 meters down and hoisting 41 meters up. At Daunia, the ratio is closer to 7.4, and the haulage fleet runs autonomously. Trucks drive themselves. Controllers sit hundreds of kilometers away in Brisbane. The people who used to sit in those cabs are now the people watching every cab on a screen at once. Open pits get the drone footage, but a big share of the world's coking coal never sees daylight until it hits the wash plant. At an underground operation south of Sydney, raw coal comes up out of the shaft and goes straight into crushing, screening, and washing, skipping the part where you dig a hole 300 meters wide across the surface. Anyone here worked underground coking coal? The rest of us reading about longwall shifts on a screen would love to hear what the crib room actually sounds like at 2 a.m. And then there is the method that eats an entire seam in a straight line. A continuous miner grinds along the coal face while hydraulic roof supports hold the ceiling up right behind it. One shift can take out what an open pit crew would call a good week. Anyone who has driven past an active mine knows the first thing you notice is not the trucks, it is the air. Coal dust travels. It coats windshields 3 kilometers away, drifts into schools, settles on laundry lines, so the mine has to catch it before it leaves the fence. Fog cannons throw fine mist 30 to 60 meters across the pit. Water bowsers soak the haul roads. Sprinklers snap on at every belt transfer point. The whole setup is not about clean coal. It is about not showing up on the evening news for the wrong reason. The pit has done its share. Getting the coal from the middle of nowhere to a steel mill on another continent is a whole other operation that runs on rails, belts, and timing nobody is allowed to lose. Once coal leaves the pit, the first mile back to the rail line is where a mine either keeps its schedule or bleeds hours it never gets back. In central India, a network upgrade tied 22 rail sidings and 5 silos into a chain of conveyor belts and rapid loading systems that skip the old truck and payloader routine. The math is telling. A rail rake that used to sit hours waiting on payloaders now gets weighed and filled straight from silo through a rapid loading system in minutes. Coal moves undercover, less dust escapes, and the mine stops depending on truck fleets shuttling between stockyard and railway siding. Move upstream from the loading silo, and the coal handling plant is where everything gets sized, weighed, and buffered. A dispatch system rated at 129.5 million tons per year runs on more than 20 handling plants, each one built around the same idea: crush, weigh, buffer, load. Raw coal drops into crushers, gets sized down, then rides kilometers of belt through transfer houses with dust suppression, belt weighers, and metal detectors. Bunkers along the way act as buffer storage so the rail loadout never runs dry. Show up late to your own train slot, and the next one sits idle on a track that burns money by the minute. Somewhere between the pit and the port, the coal has to sit for a while, and the machine that decides how it sits is easier to appreciate than to explain. A stacker rides on rails alongside a long stockpile, dropping coal in layered ribbons that keep the blend even from one end to the other. Watching a train car fill from a chute is the industrial version of watching a pitcher pour into a glass, except the pitcher is 30 feet up and the glass weighs 120 tons empty. At a Colorado mine, hoppers meter coal into each car as the train creeps beneath at walking pace. Over 100 cars per train, one after the other. The moment coal handling turns from busy work into a real operation is when the load has to hit a moving train on the mark, every time. A rail loadout in the American West sits at the end of a long conveyor run, fed from stockpiles by a chain of belts, a screening deck, and a covered transfer tunnel that keeps material off the desert wind. The loading tower is where the whole system either earns its cost or embarrasses itself. Coal drops through a chute into each car as the train rolls beneath at a fixed crawl, usually under a mile an hour. Stall the train, and one car fills lopsided. Push it too fast, and half the load ends up on the ballast next to the tracks. That is why the tower is fed by a surge bin sized to match the loading rate exactly. Belt weighers upstream hold the flow steady. Water sprays cut dust at the drop point, and the whole thing runs on a clock tied to a ship hundreds of miles away. Oh, the desert had wind today? Nobody at the dock cares. Get the train loaded and the coal is still nowhere near the buyer? It has to be lifted off the wheels, blended, and poured into a ship the size of a skyscraper on its side before that vessel starts costing tens of thousands of dollars a day just sitting there. The moment the train hits the port, the coal starts a second life, one where every minute of delay costs somebody real money. A rotary dumper grabs a full car, spins it upside down, and lets 100 tons of PRB coal cascade into the pit below. The car comes back upright, the coupling holds, the train advances. Next car up in about 90 seconds. Some ports have been doing this so long, the same dumper has been swinging cars for 15 years without a replacement. At a Colombian coal terminal on the Caribbean coast, a railcar dumper clamps a hopper car in curved arms, rotates it a full 160 degrees or so, and empties the load into a receiving pit. The clamps have to hold a car full of coal upside down without slipping. Ever tipped a full grocery bag at arm's length and felt it start to give? Now imagine the bag is a shipping container. The reset finishes fast enough to keep a whole train moving without the locomotive touching its brakes twice. Rotary dumpers were the standard for decades, and then somebody in Sweden looked at the whole idea sideways. A helix wagon system rolls each car through a corkscrew track that flips it while the train keeps moving. 25,000 tons an hour, 14 seconds a wagon, and productivity that would take 4 rotary dumpers stacked together to match. 10 years from now, is the rotary dumper still standard at every major coal port? Or has the helix idea eaten most of the new terminals? Say where you see this heading. At the Vancouver terminal, a whole train being emptied is the closest thing a coal port gets to a signature move. A rotary dumper clamps 2 cars at once, rotates them together, drops the load into a receiving hopper, then rights them and releases. The train indexes forward 1 car length. The next pair clamps in. Coal goes straight from the dump pit onto covered belts running to the stockyard. On paper, this is boring. In practice, 1 belt hiccup and a ship at the berth starts burning 5 figures a day. Not every coal port is built on the shore. Some of them are built 2.5 miles into the ocean. Abbott Point on Queensland's north coast runs a jetty 2.8 kilometers out to sea, along a coastline that gets hit by tropical cyclones on a regular basis. Coal rides an outloading conveyor the full length of that jetty before it ever touches a ship. The whole terminal was designed to move 50 million tons a year, expanding in stages from an original 15 million ton capacity. Getting there meant retrofitting new equipment into a footprint built for smaller gear, without shutting the terminal down. Trains still arrived every day. Conveyors kept running. 4 stacker reclaimers do the yard work, each rated up to 8,000 tons an hour. Each one weighs somewhere north of 1,000 tons on its own. They were built in pieces across 3 continents and shipped in for on-site assembly, which sounds simple until you see the parts turn up on a barge. At the seaward end, a ship loader over 54 meters tall waits on a second berth, ready to top off vessels at more than 8,000 tons of coal per hour. Import terminals run the same play in reverse, and the biggest bulk port in Germany does the whole loop automated, from ship unload to rail dispatch. Gantry cranes grab, bucket wheel reclaimers scoop, belts feed rail. Every step, nobody in a cab. 1 panel runs the yard. A blast furnace will not accept raw coal. Throw it in, and the whole thing chokes on volatiles, moisture, and ash inside an hour, which is why every ton of coking coal has to go through a coke oven first, and it starts at the charging car. The charging car rolls along the top of a coke battery in Bosnia, dropping crushed coal into each oven through sealed ports. The old design vented visible emissions for minutes at a time. A newer screw feeder version brought that number under 12 seconds per charge. 12 seconds versus minutes. That is the gap between neighbors calling the regulator and neighbors not noticing. Once coal is inside the oven, it gets baked without oxygen at around 1,000 degrees Celsius for 18 to 24 hours. And that is where the carbon concentrates. All the volatile stuff cooks off. Moisture leaves, tar and gas get piped out and sold separately. What is left is coke, porous, hard, and about 90% carbon. A coke plant in Ontario ran 3 batteries for 64 years straight. First fired in 1951, last push in 2015. 64 years! No off switch, ever!
One industrial installation, 3 generations of workers, one continuous heat cycle. You do not shut down a coke battery to save on the power bill. Cool it below its working range and the refractory brick lining cracks. Cracked lining is a rebuild that costs 9 figures. That is why coke plants run 24 hours a day, decade after decade, until the whole battery is finally retired at once.
The people who actually run these ovens describe the workplace as a permanent, low-grade emergency, and they are not exaggerating. At a coke works in South Australia that ran 55 years and 55 days before closing in 2023, crews dealt with jet flames up to 6 feet high, sudden oven pressure spikes, and explosions that came without warning. Their job was straightforward on paper. When something went wrong, the operator stepped out, and the maintenance crew stepped in, into flames, dust, and heat that could crack a face shield. You cannot patch a pressurized oven from a control room. Somebody has to walk up to it. Anyone here worked a coke battery crew? The rest of us reading about 6-foot jet flames on a screen would love to hear what the shift briefings actually sound like. The trade-off of that risk is coke quality that steelmakers on 3 continents pay a premium for. Every 18 hours or so, each oven in the battery hits the end of its cycle. And then comes the part that looks less like industry and more like an eruption. A pusher machine on one side of the battery lines up with the target oven. Doors on both ends open. A ram the width of the oven chamber pushes forward, and a wall of glowing orange coke, the size of a small subway car, slides out into a waiting quench car. Whoa. That is the shot cameras exist for. 20-plus tons of carbon at 1,000 degrees, sliding out horizontally in maybe 40 seconds. The heat radiates far enough that operators in nearby cabs can feel it through the glass. Timing rules every step. Push too early and the coke has not finished converting. You get soft, high volatile product the blast furnace will send back. Push too late and the next oven in the sequence backs up, the whole battery drifts off cycle, and by end of shift you are 2 pushes behind on a schedule that does not let you catch up. The quench car has under 2 minutes to reach the tower before the coke starts self-igniting in open air. The first push from a brand new battery is a bigger deal than it sounds. Everything has to align on the first try. Pusher travel, door lift, quench car position, ram thrust. Because a misaligned first push on a virgin oven can chip refractory brick before the battery has produced a usable ton. Get that wrong and you are patching a 10-figure asset before it has earned back $1.
After the push, glowing coke slides down a receiving chute into the quench tower for cooling. Water hits carbon at 1,000 degrees and flashes to steam almost instantly, a plume so dense the sky briefly turns white. 90 seconds of quench, and the coke drops onto the wharf below. Between the quench tower and the shipping yard, a lab bench decides whether the last 18 hours were worth anything. A Russian coke works walks its product through the full quality loop. Coal blending on the front end, microscope analysis on the back end, control room dashboards watching every temperature curve in between. Coke quality gets graded on 3 things blast furnace operators care about: mean size, strength after reaction with carbon dioxide, and ash content. Fine coke fractures under the weight of iron ore above it and blocks gas flow inside the furnace. High ash coke drags slag chemistry off spec. That is why the microscope on the lab bench has more say over the day than the crane driver moving 20 tons. Once the sample passes, the coke gets loaded into rail cars and heads out, most of it to blast furnaces on the same continent. Coal is not the only source of industrial carbon. Refineries produce a cousin the aluminum trade quietly runs on. Calcined petroleum coke comes from residual oil heated in vertical shaft kilns to drive off moisture and volatiles. A facility in Shandong pushes 560,000 tons a year through 640 kilns. Different feedstock, same endgame. Smelters need concentrated carbon, and they will take whichever rock delivers it.
Once the coke has cooled and passed the lab, it heads to a port that has spent decades learning how to load carbon without losing it. At a Baltic terminal, a bulk carrier pulls in under grab cranes that pluck coke out of trackside piles and drop it into the ship's holds. Every scoop weighs more than an sieve, and it moves quicker than one. Bigger coke shipments call for a capesize hull, which brings a different set of headaches to the dock. A vessel 260 meters long and 43 meters wide sits at berth while shore cranes work 5 holds in a planned sequence. Load the wrong hold first and the trim rolls sideways. The port office does not want that phone call from the captain. Sometimes one port cannot fill the ship, and the vessel has to make a second stop just to top up. A baby capesize with deadweight over 114,000 tons started its load in Gdansk, then moved to Gdynia to finish. 2 ports, 1 vessel, 2 different coke stockpiles blended into the same holds. Be honest, before this video, did you know that a single coke shipment could get blended across 2 separate ports mid-voyage? No shame either way. That call gets made by traders who never see the ship. Once coke does its work inside the blast furnace, iron pours out, and the rest of civilization starts here. At a hot strip mill in Germany, molten steel is first cast into rectangular slabs, stacked in a slab yard, then reheated to rolling temperature. The slab enters the mill glowing orange. Roughing stands squeeze it thinner. Water sprays flash off scale in bursts of steam. The finishing line has multiple stands in sequence, each one shaving the slab thinner and longer, until a chunk that started as a fat rectangle exits as strip up to 1.5 kilometers long. 1.5 kilometers of strip out of one slab. Hold on, that number does not sit right in your head the first time you hear it. That length gets coiled at the end by a reeling machine that catches strip moving at highway speed without wrinkling it. Every coil traces back to a specific batch of coke burned in a specific oven weeks earlier. Coiled strip covers the flat markets. Car panels, appliances, roofing. Rails are a different animal, and they run on a different mill. At a rail mill in northern Spain, the starting material is a bloom, not a slab. Rectangular cross-sections, 330 by 280 millimeters or 400 by 280, cast at a nearby steel shop and delivered by train. Each bloom carries its own chemistry report. Heat number, caster strand, position in the strand, all stamped on before it even reaches the reheat furnace. Because when a rail cracks under a passing train, forensic engineers work backwards through that stamped chain until they find the exact bloom. Traceability like that is not paperwork, it is legal insurance. The bloom gets reheated to around 1,200 degrees, descaled at 400 bars water pressure, then run through a breakdown stand, a tandem universal edger combo, and a finishing stand. Rails come out up to 108 meters long. Cut, then head hardened on an induction line for wear resistance. Every finished rail goes through laser profile checks, ultrasonic scans for internal flaws, eddy current for surface flaws, and a flatness gauge before shipping. The rail your commuter train runs on has probably had more inspections than most airline pilots. Flat strip and rails handle work above ground. The oil and gas industry needs something that holds up against pressure from every side at once, and that means seamless pipe. A mill in Austria starts with a solid round billet, 230 millimeters in diameter, and turns it into a tube without any weld seam anywhere on it. The trick is a cross-roll piercer. Angled rolls grip the glowing billet and rotate it while feeding it over a hardened piercing point in the center. The billet is squeezed inside out. A hole opens down its length with nobody drilling anything. Wall thickness can go as thin as 3 millimeters. From there, a mandrel bar gets inserted, and the shell is elongated up to 17 times its original length. Hollows come out up to 22 meters long, then head into a 28-stand stretch-reducing mill for their final diameter and wall thickness. Finished tubes can leave the line at 150 meters. Every pipe gets electromagnetic inspection, phased array, ultrasonic wall measurement, and hydrostatic pressure testing before it ships. A seamless pipe rated for high-pressure gas has been X-rayed, ultrasounded, and pressure tested more times than most people see a dentist in a lifetime. And then there is the steel that goes right back into mining, closing the loop on the whole chain. A specialty mill in southern India produces grinding media balls, hardened steel spheres used inside the giant ball mills that crush ore back at the mines. Capacity runs around 100,000 tons per year. Each ball goes through chemical, mechanical, and metallurgical checks before it ships. That lump of coal we followed out of a pit at the start of this video ended up as the ball that grinds the next generation of ore. The whole industry runs on itself. Every skyline, every suspension bridge, every high-speed rail corridor has a black rock buried in the accounting. Roughly 70% of the world's steel still comes out of blast furnaces, and every one of those furnaces runs on coke. The interesting argument right now is not whether coal has a future, it is which coal. Thermal demand is soft. Metallurgical demand keeps climbing because urbanization in Asia and Africa is nowhere near slowing down, and hydrogen-based steelmaking is still expensive and years from full scale. A handful of countries are quietly reopening coking coal mines that were mothballed a decade ago. So here's the real question. Is metallurgical coal simply a bridge until hydrogen steel scales up? Or will it remain the backbone of steelmaking for decades to come? Say your piece in the comments. If watching a rock become a skyscraper hit the spot, subscribe. More heavy industry rolls out next. See you. Take care.